Welcome, Mindsetters, to this another exciting session of Learn Extra Live. Guys, I hope you're ready. You know the drill. You got your pens, your pads, you're making notes. You know what? Dina, what are we going to be doing today?
This afternoon, we're going to look at the exciting properties of two quadrilaterals, the parallelogram and the rhombus. We're going to look at the properties, and thereafter, we're going to do some riders.
All right, awesome. So, guys, as I keep saying every time I open the show, make sure you got your pen and your pads out and you're getting ready to write notes. I know it's Monday, but guys, you have to keep prepping. Dina, so while you make your way over the board, I'm going to make sure these guys know where to come and find us. So guys, make sure you get on the page, www.facebook.com/learnextra. And if Twitter's your thing, tweet me at learnextra. And guys, let's get chatting, let's get going. So grade 10s, make sure you're ready for this maths lesson. Dina, take it away.
Thank you, Ty. Yeah, it's lovely to be with you this afternoon. Last week, if you recall, we did some work on triangles. And so today we're going to build up on those triangles. We're going to look at if we add another side to a polygon and we get what we call a quadrilateral, what kind of properties do they exhibit? What features do those quadrilaterals have? Now, there are quite a number of them that we investigate, and so this afternoon we're only going to have time to do two. Next week, hopefully, you'll get time to do the rest. So for now, I would like to start off with the parallelogram. And on the board, I have drawn a parallelogram, often called a palm for short, and I've listed the vertices as A, B, C, D. So if you look on the figure, starting at vertex A, B, C, and D, and notice something technical about naming a parallelogram is that we label it either in a clockwise or anti-clockwise direction. Otherwise, we're going to have this all over the place. Now, just before I carry on, I think it would be appropriate to maybe just give you the challenge question so that you can take it down, because some of you might be saying, well, I know my properties, I want to try some of the questions. So I'm going to go straight on to the challenge question, go through it with you, and then maybe you can post your answers and let's see who can actually get the answer. Right, the challenge question is as follows. We've got a rhombus, PQRS. The vertex angles have been labeled because SQ and RP, the diagonals, have been drawn. So to go through it again, PQRS is a rhombus with diagonal SQ and RP. And we have angle S1 and 2. We've got angle R1 and angle R2. We've got angle Q1 and Q2. We've got angle T1 and 2. P5 and 6, and then this vertex here, K, has got vertices 1, 2, 3, 4, 5. Okay, and the other thing that's been drawn is this line KT has been drawn to meet at T, so we also get angle T1 and 2. So if we look at the given, PQRS is a rhombus with PSR an angle of 120, so we can actually mark it in. This angle over here is 120. And then we've got PK is equal to PT. Those two lengths are the same. And your job, Mindsetters, is to calculate the ratio of angle K2 to angle K1, which is that angle over there. And that should take you a little while to get your answer through onto the Facebook page. Good luck, everybody. Let's see who the fastest mindsetter is to get that ratio. Right, and with that, I'm going to go straight back to the parallelogram. Right, A, B, C, D, and we'd like to record what the properties are. Now, obviously the parallelogram is infamous, maybe famous, should I say, for its definition of parallel. There's something parallel about the sides of the figure, and that is both sides are parallel, hence the name parallelogram. Okay, so we would say that its feature, firstly, is that the definition is that its opposite sides, let's just do it in English, so opposite sides are parallel, and in this case, we have AD is parallel to BC, and since it's both pairs, we have AB also parallel to DC. And I think we should say somewhere over here that both pairs Both pairs of opposite sides are parallel. So that's the first one. And I'm going to mark those so that our diagram fills up as we're discussing its features. Okay, so both pairs of opposite sides parallel. The second one is that there's something unique about the opposite sides, and that is that the green pair is equal and this pair is equal. So we have both pairs of opposite sides are equal. So in this case, we have AD is equal to BC, and we have that AB will also be equal to DC. Right, just finish this off here. This AB is parallel to DC. So the second property then, something about the length of the sides. So something about the nature of the sides, they're parallel. The length of the sides, they're equal. And then we're going to look at the diagonals as well as the opposite angles. Okay, in a parallelogram, the opposite angles will be equal. So B will be equal to angle D, and A will be equal to angle C. So both pairs of opposite angles equal. So our third one will be both pairs of opposite angles are equal, which means in this case, A is the same as C, and D is the same as B. And you'll see later on when we do a rider, when we actually calculate angles or we prove angles, that we're going to utilize these as reasons for putting these conditions on the figure. Because we know something is a palm, then it holds true that all these things are in fact true. And then finally, we'll look at the diagonals, AC and DB. And as I've sketched those two white lines, you'll see that AC is much smaller than what DB is. So those diagonals are not equal in length. However, if you actually had to fold your figure along AC, you'd find that B to, let's call that P, B to that point P is the same as P to D. So we talk about that length being the same as that length, and this length here being the same as that length. So we say that the fourth property is something about the diagonals, and we say that the diagonals bisect each other. Okay, so to get the two words sorted out, bisect and dissect. Dissect you use in life sciences to cut up specimens and to investigate those specimens. In maths, you bisect a segment. So a line bisects another line, and that means bi into two equal portions. So bisect, the word being used, not the word dissect. All right, so those are the properties of a parallelogram. Let's now look at how does those properties apply to a rhombus. Are some of the properties of a parallelogram found in a rhombus? And they certainly are, but a rhombus is defined as a parallelogram. So it's got parallel sides, it's got equal sides, the diagonals bisect each other, etc. But one special feature is to take the adjacent sides and make them equal. So you're basically saying the side is equal to that side. But because in a parallelogram the opposite sides are equal, it makes that side equal and it makes that side equal. So a rhombus is a specialized parallelogram. So in all parallelograms, the sides are parallel and the opposites are equal. But the moment you take one of the opposites and you make it equal to the adjacent, you've now dynamically changed that figure into a rhombus. So it's a one special case, the case where the pair of adjacent sides in a parallelogram is equal, makes it into a special quadrilateral, and that we call the rhombus. Okay, so its properties are the same. So it's got both pairs of opposite sides are parallel. Both pairs of, okay, let's just not go so fast. Let's just talk about that because both pairs are equal, but one pair of adjacent sides is equal, we actually say all 4 sides are equal. All 4 sides are equal. Then we also get that the opposite angles are equal as well. But before I put in the angles, I want to put in the diagonals, because something special happens with these diagonals of a rhombus that doesn't happen in a parallelogram. And that is that the diagonals cut each other at 90 degrees. And we've got a special name in maths for cutting at 90 degrees. It's called perpendicular. So this angle, all these 4 angles where the diagonals meet on 90, notice it did not happen in the parallelogram. And also, what this diagonal does is it cuts all these angles into equal portions. So we actually have that P1 and P2 are actually the same. And we've got that because these are all equal, this is also equal to that. So this angle over here will be 90 minus x, and this angle will be 90 minus x. And so will that one. This one will be 90 minus x, and that angle will be 90 minus x. So we have the diagonals. They bisect each other. That would make it a palm, a rhombus, perpendicularly. Okay? And fourthly, the diagonals bisect what we call the vertex angles. Okay, so that pair is equal to that pair, but because the diagonal bisects them, we have all those 4 equal, as well as those 4 angles over there equal. And that should give you some hints with the challenge question, because the challenge question was a rhombus. So the properties that you're going to be using is very much the yellow, that the diagonals bisect perpendicularly, and also that the diagonals bisect the vertex angles, as well as obviously the parallel sides and the fact that all 4 sides are also equal in length. Okay, having done the properties, let's try and prove our first rider. Right, on the board there is a quadrilateral, PQRS, which is a palm, and we're going to use palm for short. And we've also got this segment PT is equal to UR, and that's on the diagram over there. And we've got Q1, 2, 3, we've got R1 and 2, we've got this angle over here, 1, 2, 3, 4U, S1, 2, 3, and T1, 2, 3, 4. And the question, the RTP, which really stands for required to prove, we want to prove that another figure is a parallelogram. Now, before we go there, it's always extremely important to identify what portion of the given we're going to utilize in helping us frame what things we know inside that picture. So let's go to PQRS and let's say, what is it that we know about that figure? And we're actually going to put it in on the diagram. We're not going to write it down, we're just going to put it on the diagram. So PQRS is the big white figure, and if it's a parallelogram, then we're going to do 4 things. We're going to look at its opposite sides parallel, opposite sides equal, we're going to look at its diagonals, and we're going to look at its opposite angles. So let's do that. The opposite sides parallel mean that I can now place its property or its feature on the actual diagram, and we've got that this side is equal to that side, and that this side is equal to that side. And just a note, because I sometimes find people kind of merge 2 things together and begin to say things that don't actually make sense. They often say, if a line is parallel, then it must be equal to another line. That only happens because we've got a parallelogram. That doesn't happen all the time. Here I've drawn a case where a line is parallel to another, but that segment's not the same size as that segment. So lines can be parallel and yet not equal in length. They just, in this case, happen to be equal and parallel because we've got this special figure, this parallelogram. Okay. Then the next thing we want to prove is we want to show that this yellow figure is a parallelogram. And to do that, we have to utilize what we call in maths the converse. And the converse basically says that if we can prove those 4 properties that I did with you earlier, one of them, if I can show one of them is true, then that figure's a palm, and therefore the others also hold. So it's the case of having one set of those properties. And so what you're looking at now is you're saying, let's look at the yellow figure and let's see, can we prove that maybe the opposite sides are parallel? Could we do that? Because that's one of our choices. Could we maybe show that the opposite sides are equal? The diagonals have not been drawn, so I'm not going to do anything else in there. If you were just trying to investigate and to play around with quads, then maybe yes, go and do all sorts of things. But we are really trying to help structure our thoughts for an examination process. And usually within those confines, we often don't have to add anything else that is not there, unless they've given it to you as a hint. So we're not going to draw the diagonals. And maybe I could use the opposite angles to prove them equal. Okay, but I think there's quite a lot of angles there, so maybe we'll leave that for a little later. Let's rather look at, could I prove those lines parallel? Is there a way of me being able to prove them parallel? Well, I could maybe prove this set because there's one diagonal drawn, but there isn't a diagonal drawn for that. So parallel is looking rather difficult. So maybe we should try and prove that the TS is equal to QU. And I should try and prove that QT is equal to SU. And how could we do that? How could we prove that segments in geometry are equal? You did a lot of that last year in grade 9 when you worked with congruency, and that's exactly what we're going to do. In order to prove that this segment is equal to that segment, if we can show that this triangle is congruent to that triangle, then we've got it. And if you look at it carefully, can you see you've got one side is equal that we've already marked. You've got that portion that was given, that's already equal. So we're really only missing the side that we want. So that's not going to help us with congruency because we're really trying to prove congruency in order to get those sides equal. So we really do have to show something about angle R2 because angle R2 is sandwiched between 2 equal sides, and in order to prove congruency, the angle between those sides has to be equal. We can't go and find another angle. We are forced to use that angle. So do we know anything about angle R2 and angle P2? Angle R2 and angle 2P2, by nature of these parallel lines, they are actually alternate angles. So in fact, they are equal to each other. Okay. So by congruency, that length, TS, is equal to QU. And then we would do the same thing in the purple triangle. So we'd get that triangle there. Notice it's exactly the same thing. That segment, and I should really be marking the segment with 3 lines, otherwise it looks like that segment is equal to that one, which is not true. So we've got that segment. We've got this little segment here. Can you see in the purple triangle? So we're missing R1. But again, R1 is equal to P1 because they are alternate angles. So, okay. So we've got that the purple triangle is congruent to that one, which makes those 2 sides also equal. And this example shows how powerful congruency is in helping us to show that segments are actually equal in length. And because segments are equal in length, and 2 pairs of segments are equal in length, we actually have then shown that the whole figure is then a parallelogram. Okay, I think, Ty, back to you.
All right, guys, hope you've been paying attention. Hope you've been writing your notes, making sure that you remember the stuff. And guys, I am working on it. I'm going to post up the actual challenge question just now. So guys, make sure you stay tuned. And guys, before I forget, I want to send a quick shout out to Liberty. And I'm still giving away my calculator and my labeler. And before you guys forget, make sure get on the page, get chatting, get chatting, get chatting. I can't tell you this enough. All right, guys, we'll see you after this break. Welcome, Mindsetters. I hope you've had a nice little break. You've gotten yourself some snacks. You've gotten something to eat, so you don't have to get up and keep moving around because you need to pay attention. Because right now, Dina's going to explain the next section, which is very, very important. So pay attention. Dina, you good to go?
Thanks, Ty. Let's go. Right, before the last segment, you had a look at the challenge question. I'm putting it up again so that you can have a chance to look at it and work through it while we're having a small break, and you can post your answers. We'd love to hear from you and see how you're doing on the rhombus. So let's go through it again. PQRS is a rhombus with PSR 120 degrees. You've got PK is the same as PT, and we need to calculate the ratio of the sides of K2 to K1. And if any of you get that answer, then you're really smart and you get a superstar from Mindset today. Right, the picture looks as follows. There's a PQRS with its diagonals drawn so that each of the angles has got a label. And then where they intersect, it's called K, and a line is drawn from K to T. And we've got 1, 2, 3, 4, 5. And then we've got this segment PK equals PT. So if you weren't able to the last round, able to get all that, hopefully that's helped you to get on top of it. And Ty's waiting for your answer. So get going. All right. Okay. Right, but we are here to crack these geometric codes, to try and crack the given and find out how that can help us to prove what comes up next. So let's have a look at our next, what we call rider. I don't think there's an Afrikaans word for that, but most of us around the country know them as geometry problems. They're called riders. So let's have a look at the next one. We've got a triangle ABC, where AB is the same length as AC, so I'm going to put that on. And AC is produced. And just for those out there who are wanting to know more about that word, produced is a specialized mathematical word. When you have a segment and you produce the segment, then it means you've created a straight angle at the point where you've extended that line. So we know that we are able to use straight angles. If you're not told if that has been produced, you can't assume that you've got a straight angle at that point. So the word produce is very important when you read the given. It's produced to E, so that CE is equal to BD. CE is equal to BD. And then we have that DX is parallel to AC. And we need to prove that DXEC is a palm. And if we look at that, then DXEC is the figure that we are looking at. Okay, so I'm just going to dot in this little bit here, all the way there, so that you can see exactly where that figure is. All right, so the first thing I would like to find out from you is if you are given that this segment AB is the same as segment AC, then what information is that giving you? Like when we do crossword puzzles, we go to the across and the down clues, and we find the clues, and we go back to the puzzle to try and formulate the words in the crossword. What is that clue giving us? The fact that two sides in a triangle are equal. I think you remember from last week, we spoke about the isosceles triangle. And the isosceles triangle gives us base angles that are equal. So what we've actually got is that this angle over here is equal to this angle over here. Okay, so it's very important to extract the clues and put those clues physically on that diagram, because the more you're putting on the diagram, the more information you're actually seeing and the closer you are to unraveling that code, which at this stage is to try and prove that that yellow figure is a palm. Okay. Right, so that's the first little bit that's given to us. Those angles are equal. They've also given us that those segments are equal. And we've said earlier that in order to prove, and I just want to go back to those properties. Okay, we've said that the properties are these four. Okay, and if we would like to prove that we have a parallelogram, then we should be able to show that one of these is in operation. We should be able to show either that opposite sides are parallel, opposite sides are equal, opposite angles are equal, or the diagonals bisect each other. If we can show one of those in a normal quad, then we would be proving that that quadrilateral is a parallelogram. So let's actually write that up as a slide. The ways of proving that a quad, okay, so you're given a quad, and we're going to prove that that quad is a palm. So we could do it through one of the ways that we said. We've got to prove that both pairs of opposite sides are parallel. We could also prove that both pairs of opposite sides are equal. And here's a really unique way of proving a parallelogram which doesn't come from its properties, but it's one of the ways of proving a quad is a palm. It's a very useful one. If we just look at one pair, if we can prove that one pair of opposite sides is equal as well as parallel, then we have proved that it's a palm. So one pair. Whereas with the parallel sides, we have to prove two pairs. Sides equal, we have to prove two pairs. With one pair of sides equal and parallel, that is one of the ways. In fact, there are 5 ways of proving a quad a palm. Then the other one is both pairs of opposite angles are equal. And then finally, we have if the diagonals bisect each other. Okay, so whenever the question says prove a palm, you need to go and fetch one of those in order to prove that that quad is a palm. Right, so let's go back to our rider. Right, so you've now got that yellow figure, and can you see that on the yellow figure it was given to us that this side is parallel to this side, which in fact means that that ACE is a straight line, which in fact means that these yellow lines are parallel. Okay, so those sides of the yellow figure are parallel. Now if they're parallel, all that's left for us to do is either, and remember we've got a choice here, to prove that that pair is parallel, and the other way of, if you've already got a parallel side, is to show that that same pair of sides is equal. Now have a look. You've got that CE is equal to BD. That was given. Okay? So if there's a way that we could show that this little line BD was equal to DX, then do you see that we'd be talking about this green segment and this CE as being equal, and then that quad has to be a palm because one pair of sides is both equal and parallel. Okay, so is there a way that we could show that CE is equal to DX? Okay, now we've said that if there was a way of showing that these two were equal, then we would be there. So let's just see this DB. Can anyone tell me something special about AC and line DX and this line CB? Well, this is the transversal. Those lines are parallel, so what do we call these angles? Okay, they are corresponding angles. And because they're corresponding angles, this also must be x. Now you've got an interesting setup. You have dBx as an angle with two base angles equal. What does that mean in Euclidean geometry? That this must be equal to that. So we've now got that this length is equal to that length, which means that dx is now equal to CE. And so we have a nice situation here where we've shown that a pair of sides is both equal and parallel, and therefore it makes that quadrilateral parallelogram. Now, people often say that they battle with how to write it down. Where do you begin? Well, you've got to keep track of your route, because geometry is very much like a journey. You go from A to B to C. So let's look at going from Johannesburg to Durban. You wouldn't go via Namibia to get to Durban unless you were doing a round-the-world trip. But if you wanted to get to Durban in the quickest amount of time, you would climb on the highway and you take the shortest way to that town by marking off exactly where you'd be stopping. Same thing as this. This is a journey. We started off by saying, where did we start? Where did we begin? By saying that those pair of sides were parallel. And therefore, if we could show a pair equal, we would have the whole figure as a parallelogram. So you would write down that CE was equal to, or rather, that CE was parallel to dx, that was given. And you would write down that those angles were equal because you were given those sides were equal. You would write down those angles were equal because those lines were parallel and the corresponding angles were equal. And therefore, you would mark off those as equal sides, which would make that as equal to that. So can you see how I'm giving it to you step by step, how we followed that journey through to that those two green lines were equal? Okay. So we're going to see if there's any questions. And after that, we'll come back and do another rider.
So far, Paige is still pretty quiet, which is making me a little bit disappointed in my grade 10s. Guys, what's happening? What's happening? Guys, keep chatting, keep chatting. Send us those questions. Send us those questions. I am still trying to get that the actual challenge question up. It will be coming up just now. But guys, even if you're at home, you should have taken this page, you should have taken the question down and gotten it ready. So guys, make sure you keep trying. And Dina, I think, yeah, we'll go back to you then.
Okay, I'm going to put up the question again, and just to let you know that in your paper 2 at the end of the year, you're going to have 30 marks out of the 100 that are going to be based on Euclidean geometry. So it's a very easy section to get marks, because it's not like when you're solving an equation, you've got to go through all those steps of multiplying and subtracting and making sure you're collecting like terms. It doesn't get as abstract as that. You can actually see what you're doing by utilizing the picture. So it's a very visual mathematics. And as a result, you can really do well in the section. I'll never forget, once I had a student who was not able to do any algebra, but in geometry, they got 100% for the paper. So I know that for those of you who think that you battle with algebra, this might be your chance to show your potential, your true potential, by working with some visual mathematics. So here's the challenge question again. I'm still waiting for those answers to come in. It is to try and show what the ratio of angle K2 to angle K1 is. And I'm going to leave it on for a little while you're looking at the various aspects of the figure, so that I would hope to get some values from you, knowing that we've now done the rhombus, we've looked at the properties of the rhombus, and at the end of the show, I will look at the answer, but I will give you a little bit of time to just take down the features and to make sure that you can work on those values. I've given you enough information. There's enough information there for you to work with and to tell me what is the ratio of angle K2 to K1. And a little hint is really to work out what is the size of angle K1 and what is the size of angle K2. And if you've got both sizes, it will be very easy for you to see the ratio. So I think let's take a quick break and then we can come back.
All right, so guys, hope you've been paying attention, hope you've been writing your notes, making notes, and keep writing notes. But for now, guys, we're going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. And I always say, make sure you have a little snack, you have a little something, so you don't have to keep getting up. But don't drink too much water, because then you're gonna need the bathroom. When you need the bathroom, you're gonna get distracted. When you get distracted, you can't pay attention. See where I'm going with this? But for now, guys, I hope you've been sitting down writing notes. But guys, keep sending me questions. Write up what you got. If you're lost anywhere, you need help, make sure you keep sending in those questions so we can help you. So I can get those questions to Dina, and then Dina can actually help you guys. And I think, Dina, we're good to go?
Yeah, let's go, Ty. Right, everybody. Hopefully you've been thinking deeply about what these quadrilaterals are all about, especially the parallelogram, which has got so many useful properties, as well as the rhombus, which is your challenge question. I'm still waiting for what the ratio is of K2 to K1, and I'm wondering where are all the grade 10 mindsetters? Come on. I think that many of you out there can find what that ratio is, so I'm waiting for that. While we're waiting for all those answers to come in, I've taken the same question we had earlier, where PSRQ was a parallelogram, because I want to show you something wonderful about geometry, and that is that there isn't just one answer when we do geometry. There might be a variety of answers that could get us there. And we showed that this figure, we actually outlined it in yellow, this figure here was a parallelogram. And we did it by showing that this side was equal to that side, and that TS was also equal to QU. But I'd like to show you how we could also do that by showing that the lines, well, by finding a different way of proving that it's a parallelogram. And that would mean that we would need to prove that SU is parallel to QT, so we'd need to prove something about angle Q2 and angle T1. And I think that what we'll have to do is we'll have to try and prove that these triangles are congruent. And this time around, I'm actually going to write the proof down. I'm not going to talk us through it. I'm actually going to write the proof down. And remember that these portions were given as equal, and these portions were the properties of the actual quad. So this one was equal to that one. Okay. So in a congruency proof, you would always begin with one of the triangles, or listing the triangles that you're working in, and triangle SUR. Then we have that in both those triangles, PT was equal to UR. That was given. And I'm going to put my reason just a little bit on the side. There's not much space for me to write it here, so you'll see it's just next to the side and it's in brackets. Secondly, we have that this PQ was equal to SR, and you would write opposite, exactly the feature that you're working with, opposite sides of palm. Okay? And the third one, remember we said if we've got two sides, then we have to have the angle in the middle. So we would have P1 is equal to R1. And the reason that happens is because we had PQ parallel to SR. They were opposite sides of palm. Okay. So we now have that triangle PTQ is congruent to triangle SUR. And as a result of the congruency, this angle here, T4, is the same as angle U1. Let's make this A. If that is A, then this one's also A, which makes how big is T1 then? If T4 is A, then T1 is 180 minus A. And if U1 is A, then U2 is 180 minus A. So it makes this pair of sides parallel because our alternate angles are equal. Okay, so we would therefore say that our corresponding parts in the triangle, that T4 would then be equal to U1, and they would both be equal to A. But T2, actually it's U2, so U2 would then be equal to T1, would be 180 minus A. We had our straight angle. And as a result of having the straight angle, we can then say that our pair of lines, TQ, would be parallel to RSSU, because our alternate angles are equal. Okay, so and as a result of congruency, but TQ is also equal to SU, corresponding parts of congruent triangles. So we have TQ is parallel, TQ is equal, therefore our PQ, let's just do that again, because the figure that we're actually working with is TQUS. TQUS is a palm. And the reason is we've got one pair of opposite sides are equal and parallel. Okay, so that would be a second way of showing that that figure is actually a parallelogram. Okay, right, so how are we doing? Just coming back to the challenge question. Anybody got it yet? Ty, anyone got it yet?
Not as yet. They're still working on it, though.
They
That's a good sign. That's a good sign. At least you're working on it.
It does say that
So-
they're working on it. Good stuff. Okay, so I'll leave it on there for a little while longer. Let me do one more rider, and then we'll end off with this question. Okay, so we will be, here we go. Right, so we've got a parallelogram ABCD. Okay, and I'm going to stop right there. What do we know of ABCD? We know that the opposite sides are parallel. And these lines, they are straight. They've been given to us as straight lines. So we've got this whole ADY is parallel to BC as well. And we've got that ABX is also parallel to DMC. Okay. Then we've got something very interesting. We are told that BM bisects ABC, angle ABC. We talked about earlier lines bisecting each other. Now we're talking about a line bisecting an angle. So it's like a scissor. It cuts that angle in two equal parts. If we folded the angle along a line that divides them equally, then that fold is called the bisector of the angle. So the angle that we're bisecting is ABC, and over here they've said that angle B1 is X. So ABC is this angle. So what they're telling us is that this is X, and this is also X. Okay, an angle that's bisected. And then we've got that XCY is parallel to BM. So we've got that this line there is parallel to that line there. Right, and sometimes we don't only have to prove things. Sometimes they say, why don't you go and find the size of some angles in terms of a given angle or in terms of X? And that's exactly what's happened here. They said, find 4 angles that are equal to X. So let's see if we can go and find them. Okay, so we've got lots of parallel lines floating around here, which means that if I take my transversal and go along to M2, this one's also equal to X. And now that M2 is sitting on that parallel, so if I travel along its transversal all the way to C, travel along there, then this angle is also equal to X. And if we look at that line parallel to that one, then that's my transversal right there. So we've got a pair of corresponding angles. So that's also equal to x. So how many have we got? We've got the bisected angle, we've got M2, we've got C1, and we've got angle x. And you would do a neat proof, a neat logical proof with reasons as to how you've actually achieved those values. Okay, then we would like to prove that AXY is isosceles, which means this AXY triangle. So if we looked at angle x is x, then we're really trying to prove, can I show that angle y is equal to x on my picture? Because if I can show it, then this segment here is going to equal to that segment, and therefore I've been able to show that the triangles are isosceles. So in a triangle's isosceles when its pair of sides is equal, by definition, then it makes it isosceles. So will I be able to show that? Okay, so if you look at AD being parallel, then I've got this whole line is parallel to that one. Okay, and there's my transversal right here. So I've actually got an F shape going line, orange line, transversal, and line. So this angle is equal to this angle over here, but I don't know C3, but I can find C3 because C3 is sitting on this parallel line. So if I travel along C3 all the way through, then I've got this angle as x as well. So C3 is actually equal to y, and therefore, since both angles are equal to x, we've got those two lines must be equal, and therefore making that triangle isosceles. Okay, so it was all dependent on the parallel lines giving us alternates and corresponding. There's a lot of corresponding angles in F shapes, in very awkward looking F shapes that you needed to just trace your hand along just to get that exact F shape. All right, so as promised, let's look at the challenge question. Ty, anyone come up with a ratio yet?
Yes, we've got a couple.
Yeah.
Some have said the ratio should be 30 to 60, maybe 1:2.
Okay.
Couple have gotten that
Okay.
one. One person had 120 to 60,
Okay.
so I'm not too sure about that
Okay.
one. But yeah, that's what we've
120
had
to
so
60
far.
would be a 2-to-1. So I think mindset was saying that the ratio should have been 1-to-2 or 2-to-1. Well, let's calculate, and let me go through with you what where you went to with the given information. All right. Okay, so with the rhombus, let's just recap. Rhombus. Well, I'm very glad that mindsetters were at it. With the rhombus, remember that the vertex angle is bisected. Okay, that's unique to a rhombus. It doesn't happen in a parallelogram. It happens in a rhombus, that vertex angle, that line will cut that angle in half. So in the challenge question, we had 120. So it's going to bisect it into two 60-degree angles, okay, because of the property. And the other one that we've got to remember is this yellow one, where the diagonals are bisected perpendicularly. That we're also going to use. Okay, so fundamental. The diagonals behave very differently in a rhombus from a palm. Okay, let's go put that information in. Okay, so we've got a rhombus's diagonal cutting that angle. So I'm going to erase this angle over here, and I'm going to fill in the portions that we now have. So we've got that 60, that 60. Bisects. Remember, we said that it bisects it perpendicularly. So this angle is right angles, right? Okay. And then we also know that the sides are parallel, so we could work with this angle over here is 60. Okay, and if that's 60, then this angle is also 60. Okay, which makes this angle over here 30 degrees. So P6 is 30 degrees because this is now 90 with a 60-degree angle. But pay attention to PK and PT. Those two are equal, but if that's 30 degrees, then the sum of these two angles in here must be 150 because it's a triangle, angle sum in triangle, which makes this angle 75. But if that's 75 and that's right angled, then that's 15 degrees. So the ratio of K2 to K1 is 15 to 75, or a 1 to 5 ratio. Sorry, mine says, I don't know where the 6 and 30s. The 6 and 30s on the diagram, but the ratio isn't 1 to 2. It really is 1 to 5. Take that question down. Remember to keep it as study material. Use it with your friends at school. Very, very good question.
Yes. So guys, I hope you guys have been paying attention. As I always say, and hoping writing notes, I know you guys have had a little bit of trouble. I know you didn't quite get the 1:2, because that wasn't quite right, because it's 1:5. But guys, I hope you learned a lot today, as always. And guys, I can't tell you enough. Keep using the page. The page is made for you. The page is basically, think of it as study notes on click for your BlackBerry or whatever phone you're using. Because literally you can just go to the page and go through the reference material that's on the page and other people who have posted and other guys who've been chatting to you guys. But guys, for me, I'm actually going to sign off now and say, you know what, it was cool, we had fun, and you know what, we're going to see each other next week. So make sure, in fact, not even next week, just stay tuned to the channel every day, you know what I mean? So you guys can keep learning. But for me, I'm going to sign out. Peace.